We've been working on our objective, finding missing sides and angles of right triangles. So here on our Unit 9, Day 3, we've got our triangle DEF. We can see it's a right triangle. We know two sides of the right triangle, so we can find the third side by using our Pythagorean theorem. Again, Pythagorean theorem states the sum of the two legs squared is equal to the hypotenuse squared. So we can solve our equation. We know 12 squared is 144 and 7 squared is 49. All we have to do is undo this to solve for side length FE. So if we subtract 49 from each side, we have FE squared equals 95. To undo something that's squared, we take the square root, which means we end up with the absolute value of the square root of 95. From previous lessons, we know that when you take the absolute value, you're traveling the distance to the left and right of 0. So we're going to set up going to the left and right of 0 and solve accordingly. Here we would divide by -1 and divide by 1. So here are our two results. Now we have to remember, because it's a side length, we can only have a positive value. So the length of FE has to be the square root of 95. Let's replace that in our picture. So we have the three sides of our triangle. We also want to find some angle measurements. If we use angle F as our reference angle, we could label the sides based on our position. So if we're standing at angle F, we know that the hypotenuse is 12. We know our side length of 7 is opposite from where we're at, and our square root of 95 is adjacent. To find angle F, use your given side lengths to set up a ratio. So that was the opposite and the hypotenuse. Opposite and hypotenuse ratio is the sine. So the sine of angle F equals 7/12. We have to undo our sine function. With all of our functions, when we undo them, we use the inverse. So we're going to use the inverse sine to solve for angle F. The inverses undo each other, so angle F is equal to the inverse sine of 7/12. Again, making sure your calculator is in degree mode, you can enter in the inverse sine of 7/12 as it is on your paper, and we could round to the nearest degree or tenth of a degree as stated. So if we go to the nearest tenth, that would be about 35.7 degrees. We can label angle F in our picture, but we still had to find another angle measurement. So let's talk about finding the missing angle for D. So if we're standing here at angle D, now we notice that we have an adjacent and a hypotenuse given to us. The trig ratio that uses adjacent and hypotenuse would be your cosine function. So we could say the cosine of angle D is equivalent to the ratio 7/12. Again, to undo the cosine function, we can use its inverse. So we'll take the inverse of each side. Angle D will come from the inverse cosine of 7/12. And again, to the nearest tenth of a degree, that would be about 54.3 degrees. If you didn't want to use another trigonometric ratio like the cosine to solve for angle D, since we had two angles given to us, we know the sum of angles in a triangle are 180, we could have subtracted the two, 90 and 37.5, and found angle D that way as well. As always with your triangles, make sure that the largest angle is across from the largest side, smallest angle across from the smallest side, medium with medium, and you know that you're on target. Let's try another. Here we want to solve for our triangle GJH for all the missing sides and angles. Here we know two sides of a right triangle, so we could start off by finding the third missing side. Again, we could use Pythagorean theorem to help us solve for that, because the sum of the two legs squared is equal to the hypotenuse squared. Following your order of operations, we can square and take our sum and undo something that's squared by taking the square root. Again, we've got the square root of 493 equal to the absolute value of GH. With your radicals, again, make sure that you can simplify them like we've done in previous lessons, so look to see if you have any perfect square factors. Unfortunately, 493 does not, so we'll leave it as is, but you must travel left and right from 0 and solve accordingly. So that means we'd be dividing by -1 and dividing by 1 to get our lengths. We know lengths of triangles have to be positive, so we're going to have to use the length of the square root of 493 for our hypotenuse. Let's label that in our picture and use it to help find the missing side, or missing angles. So again, it's all about finding a reference. Let's say we choose angle G as our reference angle. So if we're standing at G, we could label our side lengths based on where we're located. So We know our side length JH would be opposite, side GJ is adjacent, and we have our hypotenuse at GH. Based on the givens of our side lengths of 13 and 18, adjacent and opposite, that uses your tangent function. So the tangent of angle G is equal to 18/13. We have to undo the tangent function to solve for G, so we'd have to use its inverse. So let's take the inverse tangent of both sides of our equation. These will undo each other, so G equals the inverse tangent of 18. So that's about 54.2 degrees. We're still missing another angle of the triangle. Since we know the two angles, we could find the third by taking the difference from the sum of those two from 180. So if we take 180 minus 90 minus 54.2, we could end up with 35.8. Again, if you wanted to solve it another way, you could change your location by standing at angle H. Then this would be opposite, that would be adjacent. So you could do the tangent of angle H is equal to 13/18. Use the inverse and find the angle that way. Again, here we have our right triangle KML. We want to solve for all the missing sides and angles. So we can see we have an angle of reference of K given to us. And so with a triangle, we know the sum of the angles is 180. We can take the sum of these two and the difference from 180, find your measurement for angle L, which would be 30 degrees. So if we fill that into our picture, 60 degrees. If we fill that into our picture, we now know all three angles, but we're missing some sides. Notice in this triangle, our angles are 30, 60, and 90. That's a special right triangle, and we could use the patterns with our special right triangles to solve for the missing side lengths. So again, with our right triangle here, we know that our hypotenuse is KL. Our short leg should be across from our smallest angle, which would be 249 units for LM. Our medium leg would be across from the medium angle, which is KM. And based on the patterns that we know for our 30, 60, 90s, we have some patterns that we could use to find those missing pieces. We know that the short leg times the square times 2 is our hypotenuse. And the short leg times the square root of 3 is equal to our medium leg. Well, we know the short legs. We could substitute that into both patterns and find the other two missing sides. So our short leg being 249, if we multiply that by 2, we'll get our hypotenuse. And if we multiply it by the square root of 3, we'll get our medium leg. So we can see that our short leg has a length of 498 units, and the medium leg is 249 square root of 3 units. I wouldn't worry about putting this in your calculator to get decimal equivalent. The exact value is just fine. If you didn't remember your special patterns for your 30, 60, 90s, you could have used your trigonometric ratios to help solve the problem as well. So what you have to do is, based on your givens, find a reference angle. So let's say you're standing at angle K, because that was your given. And so what we want to do is label your side lengths. So we've got the opposite, the adjacent, and the hypotenuse. So if we're standing here at angle K, we know the opposite side. So looking at the opposite side, and let's say I want to find the hypotenuse, opposite and hypotenuse would use your sine function. So we could say the sine of 30 degrees is equal to 249 over KL. If I wanted to find the side length of KM, using my givens, that's the opposite over the adjacent, and by definition, that would be your tangent function. So the tangent of 30 degrees would be equal to 249 over km. I could solve these equations and find the missing side lengths. So as you can see, we're dividing by missing sides. So again, to undo division, you would multiply to undo that. So this side I would multiply by KL. For this one, I could multiply by KM. We're trying to find the missing side length. So again, since we have a multiplication problem, same here, to undo that we can divide. On this equation, we would divide by the sine of 30. For this equation, we would divide by the tangent of 30. So these will undo. So KL would be equal to 249 divided by the sine of 30. You could round that to the nearest tenth. Also, these will undo, so side length KM would be equal to 249 divided by the tangent of 30. You could also round to the nearest tenth. Finding those values, again, using it to your decimal equivalent. Here we know that KL is approximately equals 498, like we saw before, and KM is equal to 431.3 units. If you used the first part of our problem and you multiplied by the square root of 3, this should be your approximate value back. So again, your approach could be using the special right triangle pairs or using your trigonometric ratios, sine, cosine, and tangent, to find the missing side lengths. Now that we've practiced some general triangles, let's see if we can apply them to various situations. So when you have different types of granular substances, they always naturally settle at different angles when stored in a cone-shaped pile. This angle is called the angle of repose. So suppose you have a salt pile in a storage yard that is 4 feet high. The diameter of its base is 10 feet. We want to find the angle of repose for the pile of salt. Remember, the angle of repose, by definition, is how it naturally settles when stored in the pile. So if you're dropping the salt down, it will pile up from the base up. So see how it's making an angle here with the ground. Let's draw a picture to show what's going on with our situation. So again, we talked about the angle that we're looking for, so we'll call that theta. That means we're standing here as our reference. We know that it's 4 feet tall. We also know the diameter of the base. Because it's a cone, it's a circular base. In the definition of a diameter, it's a chord that goes through the center of the circle from side to side. So that's 10. Well, a diameter has 2 pieces making up it, which would be the radii, 2 radius. So we know the radius is half that diameter from the center to the edge. Well, if the whole thing was 10, each piece would have to be 5. So this is the situation we're working with. So I can see I have 2 right triangles, and based on where I'm standing, I know an opposite, and I also know an adjacent. Well, by definition, opposite and adjacent would be the tangent. So the tangent of theta would be equal to 4/5. That's what I need to solve to find the angle of repose. So I have to undo my tangent function. We know to undo functions, we must use their inverses. So we'll take the inverse of each side. The tangents will undo, so theta is equal to the inverse tangent of 4/5. All we have to do is enter that into our calculator and we can get an approximate value. So theta is approximately 38.7 degrees. But let's say we're still doing salt piles. We want to know how tall a pile of salt be if the base now has a diameter of 40 feet. So again, let's think about what we know. We know the angle of repose from before is 38.7 degrees. We don't know the height, but we do know that we said the diameter of the base is 40, which means each radius is 20 feet. So we're looking to see about the height. So again, based on where we're at, that's the opposite. This is the adjacent. So we can use our tangent function again to help us find the height. So the tangent of the angle, 38.7, is equal to the height over 20. Again, to solve for the height, we're going to undo our equation. So we need the inverse operation of division, which is multiplication. So we can multiply each side of the equation by 20. At this point, we just need to calculate what 20 times the tangent of 38.7 is. And we can round again to the nearest tenth if we need to. It's going to be approximately 16 feet tall. Well, let's also think about what we had before. Going back to our original problem. Here, we had the height of 4, and the diameter of the base was 10. For this last problem, the diameter of the base was 40. We were looking for the height. Well, the original diameter was 10. 10 to 40, that's a multiple of 4. So if the original height was 4, if we multiply that by 4, we also got our 16. We're using the concept of similarity to also solve the problem and make sure that we're on target with the trigonometry that we were doing. So if you saw that pattern, that it was a multiple of 4, you could have just said by similar figures definition, the height should be 16 feet. Let's try another. A crane whose lower end is 5 feet off the ground has a 100-foot arm. The arm has to reach a branch which is 90 feet high. At what angle should the arm be set? So let's think about what we have. A crane, which is down here, has the lower ends. Where the operator is, they're 5 feet off the ground. So from the ground to this point here, it's 5 feet. We also know it has a 100-foot arm, so this arm here is 100, and this branch is 90 feet in the air. So from the ground up, it's 90 feet. The question is, at what angle should the arm be set? Well, here is the angle that we're looking at. So if we draw our representation, we should have something similar to what we're talking about here. Again, the crane is 5 feet above the ground, and that's where you'd be operating it from. We're looking to set the angle to that branch for the 100-foot arm. The branch is 90 feet from the ground. Well, remember, you're up 5 feet operating that crane. So technically, you're looking at 85 feet for the height that you need to cover. So if you're standing here as your reference angle, 85 is opposite from where you're standing. The 100 is your hypotenuse. Well, opposite and hypotenuse, that would be your sine function. So the sine of theta is equal to 85 100ths. We have to undo the sine function to solve for theta. Well, that means we're using an inverse. So we're going to do the inverse sine for each side of the equation. These will undo, so theta is equal to the inverse sine of 85 100ths. Rounding to the nearest tenth, we can say that's about 58.2 degrees. So in summary, we know how to find missing sides and angles for our triangles utilizing things like the Pythagorean theorem, sine, cosine, and tangent. Sometimes special triangle pairs show up like your 30, 60, 90s, 45, 45, 90s. We also noticed that we can find angles. So it says, what are you finding when you take the inverse of the sine, cosine, and tangent function? By taking the inverse of those functions, you're actually finding the angle measurements for the side ratios that are given. So that's very important to help us find some missing angles, especially when nothing else is given to us except that it's a right triangle, maybe a couple sides, and you have the 90-degree angle. That's it. So at this point, you're going to do some practice problems using the packet titled Section 13.4 that was in your folders as you came in today. On a separate sheet of paper, show me how you can complete the following problems from that packet. They start on page 795. You're going to do number 17, 26 through 31, and 52 through 57. These should be turned in to class the next time that we meet.